Hello and welcome back to my channel. This video is a compilation of questions from the topic of series from all the Cambridge International A-Level exam papers of 2020. I'll be taking you through each question, showing you the possible ways to tackle the problems. Don't forget to download the worksheet link in the description below. We're going to start with question 8 from February-March 2020 paper 12. Enjoy watching. A woman's basic salary for her first year with a particular company is $30,000, and at the end of the year, she also gets a bonus of $600. On A, for her first year, express her bonus as a percentage of her basic salary. Okay, so for part A, the bonus is $600 and the basic salary is $30,000. So we multiply this by 100. So I'll simply cancel out the 2 zeros here and also the 2 zeros here. Okay. And then 3 into 6 gets in 2 times. So eventually we get 2% for our answer. So that's the working for part A. We go to part B. At the end of each complete year, the woman's basic salary will increase by 3% and her bonus will increase by $100. Express the bonus she will be paid at the end of her 24th year as a percentage of the salary paid during that year. Okay, so let's start with the bonus. Initially, she was getting a bonus from the information we got from the question. She was getting a bonus of $600. Okay, so we're starting at $600. Then, according to the question, the bonus will increase by $100, which means that this is an AP, which is such that the common difference, D, is $100. So the $600 is the first term here. Alright, so to find how much she will get at the end of her 24th year, it's like we're looking for the 24th term. And we get that by saying A plus N minus 1D. I'm sure you know the formula for the nth term of an AP. That's A plus N minus 1D. So that's what I'll apply here. So the first term is 600 plus N minus 1, that's 24 minus 1, that's 23, times D. D is $100. Okay, so this is going to give us 600 plus 2,300, and this gives us 2,900. So this is the amount that she will be paid at the end of her 24th year. That's the bonus. Okay, let's talk about the basic salary. The basic salary, according to the question, it started out at 30,000. That's the information we have here, at 30,000. So that's $30,000. And then it is increasing at 3%, okay, at the end of each year. So this means to me that it's a GP, a geometric progression, and since it's an increase of 3%, that will be 103% as the common ratio, which is 1.03. That's the common ratio for us here. So to find the amount she will receive at the end of her 24th year, we use the formula for the nth term for a GP. So that's going to be UN is equal to AR to the N minus 1. So in our case, this is going to be A, that's 30,000, multiplied by R, which is 1.03, to the power of n minus 1, which is 23. Okay, so I'm going to calculate this. So that's 30,000 multiplied by 1.03, and that's to the power of 23. And this gives us 59,207. So I'll just write it as 59,200. So to answer the question now, they say express the bonus she will be paid at the end of her 24th year. So that's the 2,900 as a percentage of the basic salary paid during that year. So that's over 59,200, and we multiply by 100. So this will give us 2,900 over 59,200 multiplied by 100, and this gives us 4.8986. So that's to three significant figures. This should give us 4.9. So that's 4.90%. And this is the answer for part B. The sum of the first 9 terms of an arithmetic progression is 117. The sum of the next 4 terms is 91. Find the first term and the common difference of the progression. So right here, the piece of information that we have is that the sum of the first 9 terms is actually equal to 117. So that sum to 9 is 117. We've also been given that the sum of the next 4 terms is 91. Now, if we add these 4 terms to the first 9 terms, we have 13 terms in total. So the sum to 13 terms, or first 13 terms, should be 117 plus 91. So this is going to give us 208. Now, we know that the formula for sum of terms for an arithmetic progression is sum to n is equal to n over 2, 2a plus n minus 1d. So in our case, sum of the first 9 terms is going to be 9 over 2 of 2a plus 8d. The 8 is from 9 minus 1. So this is going to give us 117. I can simplify this equation by multiplying both sides by 2 over 9. So this side again by the same. So the 2's will cancel out and the 9 will cancel out. So I'll end up with 2a plus 8d on the left side. It's equal to 9 dividing into 117. It gets in 13 times, and 13 times 2, we get 26. So we have here an equation in terms of a and d. We've also been given that the sum of the first 13 terms is 208, and from the formula, that's going to be 13 over 2 of 2a plus 12d. And this is going to be equal to 208. And if I multiply both sides by 2 over 13, then the 2's will cancel, the 13's as well. So I'm left with 2a plus 12d is equal to, and I simplify this part, 13 gets into 208, 16 times. And 16 times 2, that's 32. And this is the second equation. So I can solve the two simultaneous equations by elimination. So I'm going to subtract equation 1 minus equation 2. And doing so means I'll subtract 2a minus 2a to eliminate the a terms. Then 8d minus 12d, we get minus 4d. And 26 minus 32 gives us minus 6. And if we can divide both sides by minus 4, then we will have the value of d coming out as 1.5. If I take any one of the two equations, I can take the 2a plus 8d is equal to 26, and I substitute d into it, so that's 2a plus 8 of 1.5, it's equal to 26. So that's 2a plus 12 is equal to 26, and that's 2a is equal to 14 after subtracting 12 from both sides and dividing both sides by 2, we get a coming out as 7. So we now have the two solutions. A is 7, that's the first term, and d is 1.5, that's the common difference. That's what the question wanted us to find. Each year, the selling price of a diamond necklace increases by 5% of the price the year before. The selling price of the necklace in the year 2000 was $36,000. Write down an expression for the selling price of the necklace n years later, and hence find the selling price in 2008. From the information we have in the question, we are starting with the value for the necklace, which I want to call Y0, to be 36,000. After year 1, the value of the necklace would have increased by 5%. So it's more like we're saying in dollars, 36,000 increasing by 5% is the same as multiplying this by 105%, or simply 1.05. So this will be the new value after year 1. 2 years later, we'll be increasing the value from the previous year, again by the same percentage. So it'll be 36,000 multiplied by 1.05 squared. So this is going to continue all the way until we get to year n, which will generally be 36,000 multiplied by 1.05 to the power of n. So what we have here is the expression for the selling price of the necklace n years later. Again, the question says, hence find the selling price in 2008. So in 2008, that'll be 8 years later from 2000. So that'll be Y8. So n is equal to 8. So this will be 36,000 multiplied by 1.05 to the power of 8. I'll need a calculator for this. So with my calculator, I'll type in 36,000 multiplied by 1.05, and that's to the power of 8. And this gives me 53,188. So to three significant figures, this will just be 53,200. So I'll write it down. 53,200. So that's the amount for year 8. Okay, you can write it as a currency with a dollar sign. It's still fine. So that's the answer to part A. Then for part B, the company that makes the necklace only sells one each year. Find the total amount of money obtained in the 10-year period starting in the year 2000. So here we are considering a geometric progression with first term being equal to 36,000. This is the information we have from the first part of the question, that the selling price of the necklace in the year 2000 was 36,000. So that's the first term of the GP. And again, R, which is the common ratio, we've been using it as 1.05. So for this GP, geometric progression, R is equal to 1.05. And here we're talking about a 10-year period starting from the year 2000. So it means that N is equal to 10. So if we use the formula for sum of the first n terms of a GP, which is A of R to the n minus 1 over R minus 1, then we'll be able to find the sum for the 10-year period. So we do sum to 10 is equal to A, which is 36,000, open bracket, that's 1.05, to the power of n, which is 10, minus 1, and we divide all this by R minus 1, which is 1.05 minus 1. So let's just use our calculator for the calculation. So what we're getting from our calculation is 452,804. So to 3SF, we'll just say 453,000. So that's what we get. So that's 453,000. And that's the total amount of money obtained in the 10-year period starting in the year 2000. And that's it for question number 3. The nth term of an arithmetic progression is half of 3n minus 15. Find the value of n for which the sum of the first n terms is 84. So what we've been given here is an expression for the nth term. So that's un is equal to half of 3n minus 15. So this means that I'm able to find the value of the first term and also of the common difference. The first term is u1, and that will be half of 3 times 1 minus 15, which is half of 3 minus 15, and that's minus 12. And this gives us minus 6. So since we have u1, I'm going to also find the second term, u2. That's half of 3 of 2 minus 15, which is half of 3 times 2, that's 6, and 6 minus 15 is minus 9, and half of minus 9 is minus 4.5. Therefore, I can find the common difference, D, by saying u2 minus u1. Second term, u2 is minus 4.5, and minus u1, which is a, the first term, that's minus 6. This gives us minus 4.5 plus 6, so that's 1.5. So we have here the first term is minus 6, that's a, and the common difference, D, has 1.5. So now that we have these two, the question says, find the value of n for which the sum of the first n terms is 84. So we know the formula for the sum of the first n terms of an AP. That sum to n is n over 2, 2a plus n minus 1d. So this is the formula for the sum of terms of an AP. So we'll now say that's n over 2 of 2a That's minus 6 for A, plus n minus 1 D. D is 1.5, so times n minus 1. And this should give us 84 here. I usually prefer to start by even multiplying both sides by 2 so that we do away with the fraction here. So we now have n left, and here 2 times minus 6 is minus 12, plus 1.5 times n, that's 1.5n, and 1.5 times minus 1, that's minus 1.5, and it's all equal to 84 times 2, and that's 168. So we can continue simplifying. So we have n times minus 12, that's minus 12n, and n times 1.5n, that's 1.5n squared, and n times minus 1.5, that's minus 1.5n, is equal to 168. So that means we have 1.5n squared, and minus 12n minus 1.5n, that's minus 13.5n. And taking 16 to this side becomes minus 168 is equal to 0. So I now have a quadratic equation which can be solved by the quadratic formula or otherwise. If I am going to use the quadratic formula, then A will be 1.5, B will be minus 13.5, and C will be minus 168. For convenience, but I want to use my calculator for quick working. You go to mod, then equation, that's 5, so 5. Then for quadratic, I go to option 3, so that's 3 here. So I can now store my values. So I've got 1.5 for A, then minus 13.5 for B, then minus 168 for C, which means that I can now say the first value after solving this equation, this quadratic equation, is 16. So n should come out as 16, or the second value comes out as minus 7. So n is equal to minus 7. So we have two values of n here. But since n is number of terms, it has to be positive. So n is equal to 16. So the number of terms as required by the question is 16. So that's the answer right here to this question. The first term of a progression is sine squared theta, where theta ranges between 0 and a half pi. The second term of the progression is sine squared theta cos squared theta. So on A, given that the progression is geometric, find the sum to infinity. So here, the information we have is that the first term of the progression, that's u1, is sine squared theta. And we've also been told that the second term of the progression is sine squared theta cos squared theta. So u2 is sine squared theta cos squared theta. But now on A, they say that the progression is geometric. Now for a geometric progression, the first term is A. So that will be A is sine squared theta. And the second term, we can denote it as AR. So that is sine squared theta cos squared theta. Which means that we can actually find the common ratio R by dividing the second term by the first term, which in this case will be sine squared theta cos squared theta divided by sine squared theta. So here we can cancel out the sine squared theta and we get R coming out as cos squared theta. So now that we have the common ratio, we can now apply the formula for sum to infinity. So we know that the sum to infinity of a geometric progression can be worked out with the formula a over 1 minus r, which therefore means that the sum to infinity in this case will be a, which is sine squared theta, divided by 1 minus r, which is 1 minus cos squared theta. So this means that we'll be having sine squared theta divided by, and we can apply the identity to get 1 minus cos squared theta as sine squared theta. So if I divide the two, sine squared theta into sine squared theta, the result comes out as a 1. And this here becomes the answer. So the sum to infinity in this case comes out as 1. Let's scroll down to part B. It goes, it is now given instead that the progression is arithmetic. So on B part 1, find the common difference of the progression in terms of sine theta. So the key word here is that we now have an arithmetic progression. And we know that for an arithmetic progression, the first term can be denoted by a, and from the question, that's sine squared theta. And the second term, which is denoted by a plus d, is, according to the question, sine squared theta, cos squared theta. So they say find the common difference of the progression in terms of sine theta. So to find the common difference, we subtract the second term, which is a plus d, minus the first term, which is sine squared theta. So that will be subtracting sine squared theta, cos squared theta, minus sine squared theta. So I'll apply the identity here for cos squared theta. So for cos squared theta, I'll have 1 minus sine squared theta, and that's minus sine squared theta here. Simplifying the bracket, I'll have sine squared theta multiply 1, so that's sine squared theta, and sine squared theta times minus sine squared theta, that's minus sine to the 4 of theta, and that's minus sine squared theta. And here, sine squared theta minus sine squared theta gives us 0, so we're left with minus sine to the power of 4 of theta, and this is the answer right here. Let's go to part 2. Find the sum of the first 16 terms when theta is equal to a third pi. So here we're looking for the sum of terms of an AP. And what do we have? We have the first term, that's a, as sine squared theta. And we also have the common difference, that's d, which we obtained in part 1. So d in this case is minus sine to the power 4 of theta. So that's minus sine to the 4 of theta. Now, we're being taught in the question that theta now is a third pi. So that means that a will come out as sine squared of a third pi. This is the same as sine of a third pi all to the power of 2. Now, sine of a third pi is like sine of 60 degrees. And if you know already your common trig values, the sine of 60 degrees is root 3 over 2. Now you can even use a calculator for this. So that's like root 3 over 2 squared. So we know here that root 3 squared, that's 3, and 2 squared, that's 4. And for d, the common difference, we can see that the common difference d here is minus sine to the 4 of theta, which is the same to me as minus of sine squared theta squared. It's just the same. Okay, but you see how we had obtained for a sine squared theta to be 3/4. So I can say that's like minus of 3/4 squared, which can give us minus of 3 squared, that's 9, and 4 squared, that's 16. So we now know what a is and what d is when theta is equal to a third pi. So for us now to find the sum of the first 16 terms, we can apply the formula for sum of terms for an AP. This, in this case, is going to give us 16 over 2, 2a, which is now 2 of 3/4, plus n minus 1, n is 16, so n minus 1 is 15, and d, which is minus 9 over 16. So this is what we now have. So we can just use the calculator for this. So let me do a quick working. And here I'm going to get minus 55.5. So the sum to 16 is minus 55.5. And that's the answer that we're getting here for part 2. A geometric progression has first term a, common ratio r, and sum to infinity s. A second geometric progression has first term a, common ratio capital R, and sum to infinity 2s. On a, show that r is equal to 2 capital R minus 1. So here we're going to use the information given. And since we're talking about sum to infinity, we know that the formula for sum to infinity is a over 1 minus r. That's when a is the first term and r is the common ratio. Now from the question here, they say a geometric progression has first term a, common ratio r, and sum to infinity s. So therefore s should come out as a over 1 minus r. And they also say that a second geometric progression has first term a, common ratio capital R, and sum to infinity 2s, which we can say 2s is equal to a over 1 minus capital R. So we now have these two equations. So they want us to show that r is equal to 2r minus 1. So here I'm just going to substitute the first equation here into the second equation, which means that in place of s in the second equation, I will put a over 1 minus r. So therefore, equation 2 will be like 2s. So in place of s, we have a over 1 minus r is equal to a here over 1 minus capital R. So we can simplify this now to 2 times a, that's 2a over 1 minus r is equal to a over 1 minus capital R. So solving this, we can cross multiply. So we can have 2a multiplied by 1 minus r is equal to a multiplied by 1 minus r. Then expanding the brackets, we have 2a minus 2ar is equal to a minus ar. Now you can see that the a is common for all the terms. So we can divide both sides by a. So we're left with 2 minus 2r is equal to, here we get 1 minus r. Now we want to make r the subject. So I am going to take minus r to the left side. So it's now r. And I'll take minus 2r and 2 to the right side. So minus 2r becomes positive 2r. 2 becomes minus 2. But we have the 1 here already. So that's plus 1. So we can now just simplify this to r is equal to 2r. And minus 2 plus 1 is minus 1. So r comes out as 2r minus 1. And that's what they want us to show. So let's move on to part B. It is now given that the third term of the first progression is equal to the second term of the second progression. So on B, express S in terms of A. Here they're saying that the third term of first progression is equal to the second term of second progression. So for the third term of the first progression, we are going to use the general term for an AP, which is AR to the power n minus 1. So we are going to be saying that's A, the first term, and R to the power of 2. And it's equal to the second term of the second progression. For the second progression, that will be A times R, which is capital R to the power of 2 minus 1, which is just 1. So from here, we are going to use the substitution because we had obtained in part A that R is 2 capital R minus 1. So in place of R here, we'll be having A of 2R minus 1 squared is equal to AR. And I think you can see that A is appearing in both sides, so we can divide both sides by A. So we're just left with 2R minus 1 squared, which I can now expand to give us 4R squared minus 4R plus 1. And that's going to be equal to R. And I can subtract R from both sides, so 4R squared. Subtracting R from both sides, we get minus 5R, and that's plus 1 is equal to 0. And now we have this quadratic equation, so I can factorize. So 4R squared, I'm going to split it into 4R and R. And factors of 1, I'll put a 1 here and a 1 here. And in order for us to get minus 5R, after multiplying this 2 and adding them to this 2, it means that I should be having a minus here and a minus here. So we've now factorized it, which therefore means that either 4R minus 1 is equal to 0 or R minus 1 is equal to 0. Here we get R coming out as a quarter, and here we get R coming out as a 1. So the value of R, which is the common ratio for the second geometric progression that we want, should be a quarter. So therefore, the value of R we want is a quarter. So right now, I can now take the expression for sum to infinity for the second geometric progression, and we are going to substitute R into it. So we're saying since 2s is equal to A over 1 minus R and R is a quarter, it therefore means that 2s is A over 1 minus a quarter. So let's simplify this. So this is going to be 2s is equal to A over 1 minus a quarter is 3 quarters. And this can simplify to 2s is equal to A over 3 quarters is like 4 over 3A. Okay, and we can divide both sides by 2. So if we divide both sides here by 2 and here divided by 2, then the 2's here will cancel to get 2. So we get S here coming out as 2/3 of A eventually. So this becomes the value of S. And that's how we do it with this question here. The first, second, and third terms of a geometric progression are 2p plus 6, minus 2p, and p plus 2 respectively, where p is positive. Find the sum to infinity of the progression. So what we're seeing here are consecutive terms of a geometric progression. And we know that if we divide a term by the one before it, we get the common ratio r. So here we can make use of this to help us find the value of p by dividing minus 2p over 2p plus 6. This gives us the common ratio, which again is equal to p plus 2 over minus 2p, and this is also equal to the common ratio r. So let's simplify this and see if we can work out the value of p. Now minus 2p times minus 2p gives us 4p squared, and multiplying this 2, we get 2p plus 6 bracket p plus 2. So we can expand the bracket. That's going to be 2p squared plus 10p plus 12. Now, taking everything to one side, we'll be having 2p squared minus 10p minus 12 is equal to 0. And here we can factorize, and we get here 2p and p. Factorizing and factors of minus 12, most appropriate here will be 2 here and 6. So that's plus 2 and minus 6 here. Okay, so which means either 2p plus 2 is going to be equal to 0, or p minus 6 is going to be equal to 0. Here we get p coming out as minus 1, and here we get p coming out as 6. Now that we have two values of p, the one that we want, since according to the question, p is positive, so we are going to take p as 6. So this now means that we can now find the real value of the first term, which is a. So a will be 2p plus 6, which is 2 of 6 plus 6, and this gives us 18. And the real value of the common ratio r, is any one of this. That's minus 2p over 2p plus 6. So that's minus 2 of p, that's 6, over 2p plus 6, which is 18 here. So this gives us minus 2/3. So we can now work out the sum to infinity. We know that sum to infinity of a geometric progression is found by a over 1 minus r. So in this case here, the sum to infinity will be a, which is 18, divided by 1 minus r, which is minus 2/3 here. So this means that we'll be having, that's 18 divided by 1 plus 2/3 is 5 over 3. And dividing 18 by 5 over 3, we get 10.8. And this is our answer right here. The sum S sub n of the first n terms of an arithmetic progression is given by Sn is equal to n squared plus 4n. The kth term in the progression is greater than 200. Find the smallest possible value of k. So here we've got an expression for the sum of terms of an AP. So I can find here S1, which is the first term. So that's 1 squared plus 4 of 1, and this gives me 5. I can also find S2, which is just the sum of the first two terms. So that's 2 squared plus 4 of 2, and that gives me 12. And this means that I can actually say the first term of this AP is 5, and I can also find the second term. Second term here will be S2 minus S1. And that's 12 minus 5, and that's 7. So the second term will help me find the common difference, D, where I'm going to subtract the second term minus the first one. So that's 7 minus 5, and that's 2. So we now have the first term as 5 and the common difference as 2. So for the kth term, we know that the nth term of an AP is this. Un is equal to A plus n minus 1D. So for the kth term, this will be A plus k minus 1D. But from the question here, they say that the kth term is greater than 200. So we're going to say A, which is 5, so that's 5, plus D is 2, so 2 of k minus 1 is greater than 200. So let's simplify this. This means that we'll be having, subtracting 5 from both sides. On the left side, we're left with 2k minus 2, and that's greater than 195. And if we add 2 to both sides, that's 2k is greater than 197. And divide both sides by 2, then k is greater than 98.5. Now, what we want here is the smallest possible value of k, and the smallest possible value of k, that's the least integer value greater than 98.5, should come out as 99. So the value of k that we're looking for is 99. And that's the answer right here. The first and second terms of an arithmetic progression are 1 over cos squared theta and minus tan squared theta over cos squared theta, respectively, where theta ranges between 0 and half pi. So on A, show that the common difference is minus 1 over cos to the power 4 of theta. Now, we have these two terms which are consecutive terms of an AP. And we know that if we subtract this term minus this term, then we get the common difference D. So let's do that. So I'll have minus tan squared theta over cos squared theta. And I subtract 1 over cos squared theta. So this is what's going to give me the common difference. So let's simplify this. This is equal to, I have at the bottom here a common denominator, so that's cos squared theta. So I'll have at the top minus tan squared theta minus 1. And this is the same as minus of tan squared theta plus 1, and it's all over cos squared theta. Now we know from our identities that tan squared theta plus 1 is the same as sec squared theta. So it's more like we have minus sec squared theta over cos squared theta, which I'll write as divided by cos squared theta. And here we know that sec squared theta is like 1 over cos squared theta. And when we say divided by cos squared theta, that's the same as times 1 over cos squared theta. And this is going to give us minus of 1 over cos squared theta times cos squared theta gives us cos to the power 4 of theta. And this is the answer. Let's move on to part B. On part B, find the exact value of the 13th term when theta is equal to a 6th pi. So here we know that the nth term of an AP is found by A plus n minus 1D. So here we'll be saying the 13th term is going to be a, which is the first term. And the first term is 1 over cos squared theta. So it's going to be 1 over cos squared theta. And that's going to be plus n minus 1, which is 12 of d. And we had gotten d to be the common difference. That's minus 1 over cos to the power 4 of theta. So let's put it here. So that's minus 1 over cos to the power 4 of theta. So let's simplify this. But now we've been given that theta is equal to a 6th pi. And we know that when theta has a value of a 6th pi, then cos of a 6th pi gives us root 3 over 2. And therefore, cos squared of a 6th pi should be us squaring this. So this should give us 3 over 4. And also, cos to the power 4 of a 6th pi should give us, we again square this, so we get 9 over 16. So if we apply this here, then we have the 13th term coming out as 1 over cos squared theta, which is cos squared of a 6th pi, which is 3/4. So it's 1 over 3/4. And that's plus 12 of minus 1 over cos to the power 4 theta. And cos to the power 4 of a 6th pi is 9 over 16. So it's minus 1 over 9 over 16. So this simplifies to 1 divided by 3/4 is 4 over 3. And this is 12 of minus 16 over 9. And this simplifies to 4 over 3. And then here we'll be saying 3 into 9, we get 3, and 3 into 12, that's 4. And 4 times minus 16, that's minus 64 over 3. And we know that 4 minus 64 is minus 60, and minus 60 over 3. Eventually, we get 3 into minus 60, that's minus 20. So the answer comes out as minus 20. And that's how we do it.